Greetings, I am Dr. Beyond, and I welcome you to the multiverse. From modern literature, we've been programmed with the belief that space is the final frontier. As you fly through this complex world of fractals, notice the most important thing. This is the creation of our mind. Our mind is the final frontier, the imagination driven by fractal geometry. You've heard many times the concept of the word fractals, and how does that relate to biology and evolution? Let's understand what a fractal is. It's geometry. What is geometry? The mathematics of how you put structure into space. So if we want to talk about nature, the structure and evolution of nature, the physical nature, how do we put that into space? Well, we would need to use the mathematics of geometry. But the geometry that we all learned in school was called Euclidean geometry. You're familiar with that one. That's the one that had cubes and spheres and cones and flat planes and straight lines and points. But what did we create with that structure? The buildings we live in, the machinery that we have built. Man-made objects are coming from Euclidean geometry. But you know what's interesting? You can't create nature with Euclidean geometry. It was in the mid-1970s that mathematician Benoit Mandelbrot, working at IBM Laboratories, brought forward from the past an understanding of mathematics that he gave the name fractal geometry. The idea of fractal geometry wasn't created by Mandelbrot. In fact, the idea of fractal geometry was from the late 1700s. Why did it take so long for fractal geometry to come into our world? Well, the answer is profoundly simple. When you create geometric objects, we put it on paper, such as graph paper, and you use points. And the idea is every time you solve an equation, you put a point on that graph paper. The issue is this. To actually see what a fractal looks like from that geometry, it takes thousands to millions of points just to see what the image looks like. Consider that possibility. If you're the mathematician and you wanted to see what a fractal looked like, it would take you years working every day, all day long, creating points until you could step back and see what a fractal looked like. Well, no one saw a fractal. It was in their mathematical imagination. But in the mid-70s, that's when Mandelbrot, working at IBM, had access to the latest, most powerful computers. And what did he do? He put the information of fractals from ancient mathematics into that computer. And when he resolved the images that came from fractals, it blew his mind. Because for the first time, there were mathematical equations that actually created what looks like nature. It created organisms and trees and shells and plants. And it was all from mathematical equations. And so all of a sudden there was an understanding that nature was built out of fractal geometry. But what is fractal geometry? Well, I can tell you very simply this. The geometry that you learned from the Euclidean mathematics was all based on what are called units of dimension. So the idea is an object can have 3 dimensions, such as a cube or a sphere. It can have 2 dimensions, such as a flat plane. It could have 1 dimension as a single line. And in fact, there's even something called 0 dimension, which is just a point. And I say, well, interesting, using this mathematics, we work with whole units of dimensions. 3, 2, 1, even 0 dimensions. But what's interesting about fractals is it requires a whole different geometry. And to give you an example of what I mean by that new geometry, let me show you this. I start with a piece of paper, which let's just say represents a 2-dimensional object. And I crinkle that piece of paper up, and now you look at it and it says, oh, it's a 3-dimensional object. I go, well, interesting, that's an illusion, because it's not really a 3-dimensional object, and it's no longer just a 2-dimensional object. It's somewhere between 2 and 3. It's a 2.5-dimensional object. Again, look at this. Here's a flat plane, which represents a 2-dimensional object. But as you can see, as I pull off the string, it's all actually just 1-dimensional objects looking like 2-dimensional plane. Point again. No longer is it a 1-dimensional string, nor is it a 2-dimensional surface area. It's a 1.5 dimensions. And all of a sudden I say, wait a minute, These are fractions of dimensions, not whole units like 1, 2, and 3 dimensions. It's like 1.5, 2.5, 3.5 dimensions. I say, oh, you need a new geometry. You need a geometry that deals with fractional geometry. Fractional geometry? That's the base word for the concept called fractal geometry. But what's unique about fractal geometry is this. It's all based on just one simple equation that is repeated over and over and over again. It's called an iterated equation. So basically what you do is you have an equation, solve that equation, and take the answer from that equation, feed it back into the equation, and solve it again. Get another answer, feed it back into the equation, and solve it again. And so basically you can do this infinite number of times. I'll give you a simple understanding that you probably played with in your mind years ago, and that is this. Take a line, cut it in half. That's the equation. But then you take the result from that cutting in half, put it back into the equation. So now I have a different line, and I cut that in half. And then I get the result, I get a smaller line. So let's say I start with a 1-foot line, and I cut it in half, now I have a 6-inch line. Now I say put that 6-inch back into the equation, cut it in half, what do I end up with? A 3-inch line. And then I say, yeah, take that 3-inch, put it back in the equation, cut it again, now you end up with a line 1.5 inches. I say, how many times can you do this? Infinitely. So the beautiful part about a fractal is just basically mathematics, including multiplication and addition as the primary element of the equation. And when you repeat this equation, you actually start to get images you can put on a piece of graph paper and chart what this ultimate geometry will look like. So the concept of an iterated equation, a repeat equation, is the foundation for this. And so what we're going to show you now is what does a fractal look like as you move through this fractal. And you can see how great the complexity, but you can also start to see the organic character of this fractal. Well, look, here's a picture of a mountain with clouds. You know what? It's not a real picture, it's a mathematical equation. You can reproduce nature, a mountain with clouds on it. And here's another fractal, and this one looks like a fern plant. It's exactly like a fern plant, except what? It's a mathematical equation. And here's a real live fractal you may have seen in your grocery store. It's called Romanesco broccoli. Now, when you look at this image, what do you see? All these little pyramid-shaped lumps. But guess what? On every pyramid-shaped lump, there's a smaller lump. And if you can magnify it, the smaller lump has the same structure as the larger lump. The example provided by Romanesco broccoli is the principle of fractal geometry. The images in fractal geometry are based on using the same equation and repeating it over and over and over again. The consequence of that repetition is that the structure of the fractal repeats itself at different levels of organization, from a microscopic level to the macroscopic level. Once a pattern is established in a fractal, it's repeated in a self-similar fashion at every level of organization. There's an ancient saying, as above, so below. This is exactly the principle built in to fractal geometry. It's a principle that says if you look at any structure in a fractal field and understand its organization, you will find that that organization will repeat itself either at lower levels of organization or at higher levels of organization. In biology, this is so clear from this simple fact. A human body is made out of 50 trillion cells. The cell is an equivalent of a miniature human. Why? Every function that you have in your human body is already present at a more simple level in a single cell. A cell has a respiratory, digestive, excretory system, musculoskeletal system, endocrine system, reproductive system. A cell even has an immune system. I say, why is it relevant? Because a human is a geometric fractal associated with a cell. We're made out of cells, and yet our structure has all the functions of cells. And the significance of that is, if you want to understand how a human works, do you have to understand the human physiology? And I go, no, this is why we study cell biology, because in a simpler form, you can get the foundation of what really creates the complexity of a human, and recognize that in that complexity of the human is the same structural foundation is found at the smaller level of the fractal. Significance of understanding fractals now in regard to understanding evolution is that A, nature is fractal in its structure. B, that nature evolved from a very primitive state to a much more complex state. C, because of self-similarity, if we look at the level of the fractal below a human or above a human, we can understand who we are, how we got here, and where we're going. Why? Because fractals reveal pattern. Pattern is how you can see the world and where it's come from and where it's going if you have a pattern. And now we have an understanding that human evolution is a fractal pattern of animal evolution. And the significance of all that comes down to, well, if we understand the nature of animal evolution, then we're also given insight to the future of human evolution. And here's another interesting fact. It's an established fact of mathematics. If you want to model two-dimensional surface area into a three-dimensional space, you require fractal geometry. And so it's not strange that nature is itself fractal because it's revealing the expansion of intelligence. And intelligence's fundamental level is a two-dimensional surface area called the cell membrane. And when we model the story of the membrane, we see that evolution wasn't one continuous, slow, imperceptible gradient from a simple organism to a complex organism. What we saw was very much important new insight. It's that evolution has start and stop points that repeat. Start, create something, stop, create something in a different fashion, stop, start again, and repeat. And I say, why is that relevant? Because then when we understand where we are, human civilization at this moment is in an evolutionary upheaval because we're creating a new start point of this evolutionary paradigm. The first phase of human evolution was to make the smartest human possible. How much brain can we put in a skull? And with all the folding, the sulci and the gyri, we can pack in a lot of surface area, which is the equivalent of membrane. And I say, then the evolution of humans stopped. Why? You couldn't put any more brain into the skull. And I say, well, that was the first phase, make the smartest human. What's the second phase? And I say, this is why it's so important, because we are in the second phase. And what is that second phase? The assembly of smart humans into a community to share awareness, a community that will collectively create a new organism. Yes, the human has finished its evolution like the cell. And when the cell finished its evolution, it joined into a community, 50 trillion of which make up a human body. And now what? Well, the human as a cell is complete. And what's the next level of our evolution? We're seeing it right now. The coming together of all humans into one superorganism called humanity. To do what? Share the collective awareness to make something new and bigger. And that's where we are today. So when you see the world look like it's falling apart, guess what? It is falling apart. But it's not bad news. Fractal geometry is creating a whole new structure of human evolution. This structure is the coming together of all of us into one functional organism called humanity. Each human is a cell in the body of the evolving new humanity.